Hello students, I hope you all are doing good. So our today's topic is electromagnetic induction NCERT exercise. This is the disclaimer. Learning objectives. After this lecture, you will be able to understand how to calculate the induced EMF using Faraday's law of electromagnetic induction in different scenarios. Apply the concepts of magnetic flux, rate of change of current and area to determine induced EMF and currents. Recognize the relationship between self-inductance, mutual inductance, and changing currents in coupled circuits. Calculate the duration and direction of induced EMF based on the motion of conductors through magnetic fields. The index. There are total 8 NCERT exercise questions in chapter electromagnetic induction. In today's lecture, we are going to cover all the questions, that is from 6.1 to 6.8. So let's begin with first question. So predict the direction of induced current in the situation described by following figures 6.5 A to F. So 6 figures are given. You have to determine the direction of induced current. And how can we do it? By using Lenz's law. Okay. So we have done this previously in the Lenz's law also by taking a loop and magnet orientations. Now there is many type of configurations are there, having tapping keys or having rheostat, having two solenoids. Okay, so these 6 figures are given. I will give you some time to think about it, then we will move up to the solution. So let's see the solution. So direction of induced current in a closed loop is given by Lenz's law, as I have already mentioned. And Lenz's law states that the direction of induced current is such that it opposes the change in flux. Okay, change in flux, either increase, either decrease, due to which it is produced. Okay, so it will always oppose the cause due to which it is produced. And what is the cause here? Change in flux. So in every case, there will be change in flux. Okay, either increase, either decrease, due to which EMF will be induced such that it will oppose the increase or decrease in the flux. So there is a figure 6.6 illustration of Lenz's law that we have discussed in the Lenz's law also. So when north pole is moved towards the coil, what will happen? What is the cause? Now, north pole is moved towards the coil, magnetic field lines that are passing through the coil will increase. So magnetic flux linked with the coil will increase. So magnetic flux is changing, EMF will induce, that is current will induce, and the cause of this induction of the current is motion of the magnet. So current will induced in such a way, it will oppose the motion of the magnet. So north pole will be induced. So this is the representation of north pole. If the direction of coil is anti-clockwise, if you are viewing from the magnet side, if you are viewing from the another side, it will look like clockwise. So we are viewing from the magnet side. Okay, so it is looking like anti-clockwise. So anti-clockwise means north pole. So north pole will be generated facing the north pole of the magnet. So it will repel the magnet and oppose its motion. Okay. In the second case, when north pole is moved away from the coil, then magnetic field lines and hence magnetic flux through this coil will decrease. Okay. So the direction of induced current will be such that it will oppose the motion of this magnet, due to which magnetic flux is changing. So north pole is moving away, so south pole will be generated, clockwise current will be generated, due to which it will attract the magnet and oppose its motion. Okay, so clockwise current is linked with south pole, anti-clockwise is north pole. Okay, okay, so moving north pole towards the coil and moving south pole away from the coil having similar effects. Okay, and moving north pole away from the coil and south pole towards the coil will be having similar effects also. Okay, so in both cases south pole will be generated, and in above both cases, when north pole is moving towards the coil and south pole is moving away from the coil, the pole generated will be north. Okay, so these are the basics. Now let's do for figure A. So in figure 6.15a, south pole of the magnet is moved towards the coil. So if south pole is moved towards the coil, then which pole will be generated to oppose the motion of the magnet? South pole should be generated to oppose the motion. So south pole of magnet is moved towards the coil, which increases the flux through the coil. Okay, and this induces the current in the coil. Flux is increasing, current will be induced. Direction of current will be such that it repels the magnet, it opposes the motion of this magnet. So to oppose the motion, it is only possible if south pole will be generated on the side of the magnet. So it will oppose the motion of the magnet. Okay, so what is the direction of current in the south pole? Clockwise. So like this, clockwise. So like this. Okay, so induced current flows in clockwise direction in the coil when viewed from the magnet side, not from the away from the magnet side. From the magnet side, the direction of the current will be clockwise and south pole will be generated. Thus direction of induced current is from like this, Q R P Q. Got it? Now in second figure B, now two coils are there, another coil has been inserted. So south pole is moving towards the coil and this magnet is, north pole is moving away from the another coil. Okay, in both cases south pole is moving towards this first coil PQR. Okay, so south pole will be generated on the side of magnet and north pole is moving away from this XYZ coil. So now north pole moving away and south pole moving towards, having similar effect. So south pole will be generated on the side of magnet in the second coil also. Okay, so in a figure 6.15b, south pole is moved towards the one coil, that is loop PQR, and north pole is moving away from the coil, another coil, that is loop XYZ. So for loop PQR, south pole is moved towards the coil, so flux through the coil increases and this induces the current in the coil. Okay, so according to Lenz's law, direction of induced current is such that it repels the magnet. So, and it is possible only when south pole is generated on the side of the magnet. Okay, so induced current flows in the clockwise direction when viewed from the magnet side. Thus direction of induced current in the loop is, now this loop is in the downward direction now. So direction of induced current will be clockwise. So this outer part of the coil is connected to the outer part of this circular coil is connected with the rectangular coil. So current will flow in the clockwise direction, means current is flowing from PRQ and in this circular loop in the clockwise direction. So current will be in the direction from PRQP. Okay. Now for loop XYZ, north pole is moved away from the coil. So flux through the coil decreases, which induces current in the coil. So direction of induced current is such that it attracts the magnet, because direction of induced current will be such that it will oppose the motion, and this north pole is moving away from the coil, this coil XYZ. So it will try to attract it to oppose its motion. Okay, so north pole direction of induced current is such that it attracts the magnet, so that, and it is possibly only when south pole is generated on the side of the magnet. So south pole of the coil faces the magnet. So induced current flows in clockwise direction in the coil when viewed from the magnet side. When viewed from the magnet side, on this end, the direction of the current will be clockwise. Okay. On the other end, if you are not able to visualize that end, you can see on the other end. So on the other end, which pole will be generated? North. If in this end, at this end, on the side of the magnet, south pole is generated. So on the other hand, north pole will be generated. Okay. So north pole means anti-clockwise direction. So like this. So it will go like y, z, x, y. Okay. So you can see the direction by this only. So also direction of the induced current in the loop is along y, z, x, y. Okay. If you are not able to visualize that end, so if you have confusion in determining the current in that end, you can determine the current in that end, in the another end. Okay. If on one end there is south pole, then on other end there is a north pole, and direction for north pole is anti-clockwise. So current is flowing from y, z, x, y. Okay. Now third, C. In figure 6.15C, as the tapping key is closed. Now in the C figure, as the tapping key is closed, current will start from 0 to its maximum value. Current will start flowing and go from 0 to its maximum value. Now you can see current is flowing like that. So when viewed from this XYZ coil, it is in the clockwise direction. Okay, so the current start flowing through the circuit. So initially current will increase from 0 to a steady maximum value. When viewed from the anti-clockwise direction, this direction. This shaded part, this light arrow is in the outward direction. This dark arrow is in the inward direction. So when viewed from another coil side, this XYZ coil, direction of the current in the is anti-clockwise, and hence north pole is formed. Okay. Since current is increasing from 0 to maximum value, so strength of north pole will increase. Since current is increasing, strength of north pole is also increasing, due to which flux through the coil is also increases. So magnetic flux is increasing. To oppose the magnetic flux, to oppose the increase in the magnetic flux, hence according to Lenz's law, current will be induced in another coil XYZ such that it will repel the circuit away from it, so that the increase in the magnetic flux will be neutralized. Okay, that is north pole will be formed. Okay, how it will repel this circuit? When north pole will be generated in the XYZ coil. So how north pole will be generated? When direction of current will be anti-clockwise, that is from ZXYZ, like this, or we can say YZXY. Okay, anti-clockwise direction. So direction of induced current will be anti-clockwise in this coil. Okay. Now D. So in this figure, you can see the reading of the rheostat. Reading of the rheostat is increasing. Like you can see in the arrow also, it is being increased. Means resistance is being increased. Okay. So in figure 6.515D, value of resistance is being increased. This pointer is moved to the higher resistor value. So resistance is being increased with the help of rheostat, due to which current is decreasing. If resistance is increasing, current will decrease in the coil. Now you can see direction of current in this coil is, when viewed from this side, XYZ coil, direction of current is anti-clockwise, that is north pole, and current is decreasing. Since current is decreasing, the strength of the north pole will decrease. Direction of current in the coil is anti-clockwise when viewed from another coil side. Therefore, strength of north pole is decreasing with time. So according to Lenz's law, flux through the coil is decreasing and current will be induced in another coil in such a way south pole will be formed. So strength of north pole is decreasing. So magnetic flux through this XYZ coil is decreasing. So it should have to support the magnetic flux to neutralize the decrease in magnetic flux. So which pole will be generated? South pole. Okay. So south pole means clockwise direction. So from y to x, x to z, z to y. Okay. So direction of induced current will be clockwise. That is along y, x, z, y. Okay. Now E part. Tapping key is released. It is similar to previous question. Okay. Tapping key is released. Current will decrease from maximum to 0. So in figure 6.5e, direction of current in the first coil will be anti-clockwise. So when key is connected, current is flowing through that. So this shaded part is, this dashed part is other side of the coil. So like this. So current is flowing like this. Firstly, it will go in the dashed line and then come in the outward direction. So it is anti-clockwise. When viewed from this XYR coil, okay, it is anti-clockwise. Means north pole is there on this end. Okay, so anti-clockwise and viewed from another coil side, that is north pole is formed. Since the key is released, that means current will decrease from maximum to 0. That means strength of north pole will decrease and flux through the coil will decrease. This is similar case as in the previous diagram, as in the previous case, in the D case. Okay, so the pole that will induce on the side of this coil will be south pole. Okay, so according to Lenz's law, current will be induced in another coil is such that south pole is formed. Okay, hence direction of induced current will be from now south pole is being formed, so direction of current will be clockwise in the that end, on the side of x, where x is written on that end, direction of current will be clockwise. On the another end, direction of current will be anti-clockwise, means north pole. So you can see like this, north pole. So current is going from x to r to y to x. So x r y x. Okay, in this case, now straight conductor is given. So magnetic field lines for a straight conductor is concentric circles. And direction of magnetic field is always perpendicular to the direction of current at every point. So in figure 6.515f, magnetic field lines around the straight conductor, current carrying conductor will be in the form of concentric circles. These magnetic field lines are lying in the plane perpendicular to the direction of the current. So all the magnetic field lines will be in the plane perpendicular to the direction of the current. So hence no current is induced since the magnetic field lines are lying in the plane of closed loop. So this is closed loop. We have to find the magnetic flux through it. Since magnetic field lines are in the same plane, that means B dot A, theta. Theta is the angle between the area vector. Area vector will be perpendicular to the loop. Okay. And magnetic field is in the plane of loop. So angle between area vector and magnetic field is here 90 degrees. So BA cos theta, BA cos 90 degrees, 0. Cos 90 degrees 0. So there is no flux through the coil. So hence no EMF will be induced in through the coil. In this case, magnetic flux through the closed loop is 0. So while the current is decreasing, so magnetic field flux will be 0 all the time. So change in magnetic flux is 0. Therefore, magnetic flux through the closed loop is 0 and no current is induced in the case F. So next question, exercise 6.2, use Lenz's law to determine the direction of induced current in the situation described by figure 6.16. First case is when wire of irregular shape is turning into a circular shape and when a circular loop is being deformed to a narrow straight wire. Okay, in both the cases, area is being changed due to which magnetic flux will change. So you have to find the direction of induced current according to Lenz's law. I will give you some time to think about it. Okay, so let's see the solution for first diagram. So according to Lenz's law, the magnetic flux produced by the induced current opposes the cause of induction. That we all know. Okay, it defines the direction of the flow of induced current. So in the given closed loop, the loop is placed in magnetic field and it is changing its direction from irregular to circular. So irregular shape has less area than the circular shape. Okay, so magnetic flux is increasing since area is increasing. Okay, so during this change, magnetic flux linked with it increases. Okay, since magnetic flux is increasing, so according to Lenz's law, the induced current should produce the magnetic flux such that it reduces the flux linked to the coil. So flux is increasing, so induced current will be such that it will reduce the flux that is being increased. So induced current will produce the magnetic flux that will reduce or oppose the flux linked with the coil due to the magnetic field. Okay, so induced magnetic field should be in the opposite direction to the original field. Magnetic flux is changing, or we can say increasing. So to neutralize the increase, mag- that induced magnetic field should be in the opposite direction to the original field direction. Thus, the current should flow in the anti-clockwise direction. Now, if the original magnetic field is in the inward direction, so induced magnetic field should be in the outward direction to neutralize the increase in the magnetic flux. So point your thumb in the outward direction and curl your fingers. Your finger will curl in the anti-clockwise direction. So induced current should be in the anti-clockwise direction in the coil. That means from A to D, D to C, C to B. So direction of induced current will be A, D, C, B, A. Okay. Now B part. Now, circular coil is being deformed into a narrow straight line. Means magnetic flux is being decreased. Okay. So now magnetic flux is decreasing. So induced current will be such that it will produce magnetic flux that will try to neutralize the decrease, that will support the existing magnetic flux. Okay. So as the circular loop is being deformed into a narrow straight line, the magnetic flux linked to the loop will decrease. And according to Lenz's law, the induced current should oppose the cause of change. So flux will be induced such that it will increase the original flux. So it will try to increase the original flux. It will support the original flux so that it can neutralize the effect of decrease of original flux. Okay, so induced magnetic field lines should be in the same direction of the original field direction. So original field direction is represented by dot here. That means it is in the outward direction. So induced magnetic field should be in the outward direction. So point your thumb in the outward direction and curl your fingers. Thus the induced current should be flow in the anti-clockwise direction. Okay, that is from that dashed line. A dash, D dash, C dash, B dash along anti-clockwise direction. Got it? Next question. Exercise 6.3. A long solenoid with 15 turns per centimeter has a small loop of area 2 centimeter square placed inside the solenoid normal to its axis. Okay. So this is not a separate area. This is the area of cross section of solenoid only. Only they have twisted the words. Okay. So this is the cross sectional area of the loop that is perpendicular to its axis and having value 2 centimeter square. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 second, what is the induced EMF in the loop while the current is changing? Okay. So I will give you some time to think about it. Let's see the solution. So number of turns are given. Per unit length is given n equal to 15 turns per centimeter equal to 1500 turns per meter. Okay, number of turns, length of solenoid is not given. So we have assumed 1 meter. So capital N is equal to 1500 turns if we assume 1 meter length of solenoid. Okay, so it is of no use actually. So area of solenoid A equal to 2 centimeter square equal to 2 into 10 to the power minus 4 meter square. So current carried by the solenoid changes from 0 ampere to 4 ampere. That means change in the current of the solenoid is di, which is equal to 4 minus 2, 2 ampere. So change in the time is 0.1 second, dt equal to 0.1 second. Okay. So magnitude of induced EMF epsilon in the solenoid is given by Faraday's law as epsilon equal to d phi b upon dt. Okay, NCERT equation 6.3. So where d phi b is the change in the flux. So according to Faraday law, induced EMF is equal to magnitude of induced EMF is equal to rate of change of magnetic flux. So d phi b is the change in the flux through solenoid and dt is the change in time. So magnetic flux through the solenoid phi b is given by BA. Magnetic field solenoid due to solenoid magnetic field is given by B equal to mu naught Ni, where N is number of turns per unit length, I is the current flowing through it. Okay. Now, where mu naught is equal to permeability of free space and equal to 4 pi into 10 to the power minus 7 Henry per meter. Henry per meter is the another unit. Okay. So now, in the place of phi B, we will put BA. Okay. So hence EMF equation reduces to epsilon equal to D. In place of phi B, we are placing BA upon dt. Okay. Now, area is constant. So it will come out magnetic field is equal to mu naught Ni for solenoid. Mu naught is constant, number of turns per unit length is constant, but current I is not constant here. Okay, so mu naught Na will come out of the derivative into di by dt because current is changing with respect to time. After substituting all the values, so epsilon equal to mu naught is 4 pi into 10 to the power minus 7 into 1500 into 2 into 10 to the power minus 4 into 2 upon 0.1. 2 is the change in the current and 0.1 is change in time. So epsilon equal to 7.54 into 10 to the power minus 6 volt. This is the amount of EMF induced in the solenoid. So hence the EMF induced in the loop is 7.54 into 10 to the power minus 6 volt. Okay. So next exercise 6.4, a rectangular wire loop of side 8 centimeter and 2 centimeter with a small cut is moving out of region of uniform magnetic field of magnitude 0.3 Tesla directed normal to the loop. Okay, so magnetic field is directed normal to the loop and normal have two sides 8 centimeter and 2 centimeter. So what is the EMF developed across the cut if velocity of the loop is 1 centimeter per second in a direction normal to? There are two cases: when velocity is perpendicular to the longer side, when velocity is perpendicular to the shorter side of the loop. Okay, you have to find the induced EMF in two cases. Now you have to find one more thing: for how long does the induced voltage last in each case? For how much time induced EMF will remain as it is? Okay, for how much time EMF will be induced? So I will give you some time to think about it. So length is given. 8 centimeter, that is 0.08 meter. Width is given b equal to 2 centimeter, 0.02 meter. Hence area of rectangular loop A equal to L into B, which is equal to 0.08 into 0.02, which is equal to 16 into 10 to the minus 4 meter square. So magnetic field is also given b equal to 0.3 Tesla, and magnetic field is uniform, means magnetic field is having same value in the region at every point. Velocity of the loop is v equal to 1 centimeter per second, and we can write in the SI units 0.01 meter per second. So two cases to consider. First case will be motion normal to the longer side, that is 8 centimeter, and case B will be motion normal to the shorter side, that is direction of velocity will be normal to the shorter side, that is 2 centimeter. So let's do first case, motion normal to the longer side. So this is diagrammatic representation. So this is a loop having length L and breadth B, and the direction of velocity is perpendicular to the longer side, that is L. It is going in the outward direction from the magnetic field. Okay. Now EMF developed in the loop is given as, so motional EMF, expression for motional EMF, epsilon equal to BLV. B is the magnetic field, L is the length perpendicular to this velocity, and V is the velocity. So NCERT equation 6.5 equation. So after substituting all the values, epsilon is equal to 0.3 into 0.08 into 0.01. So epsilon is equal to 2.4 into 10 to the minus 4 volt. Okay, so this is the EMF. Now we have to find for how much time EMF will last in each case. Okay, so now this, if this loop is at end of the magnetic field, but there is a maximum flux through the coil, means loop is wholly in the, is completely inside the magnetic field, but just after it start to come out of magnetic field, and how much distance it has to cover to completely come out of the magnetic field, that is B, width. That is the minimum distance loop should cover to come completely out of the magnetic field. Okay, so time taken to travel along the width, that is T, equal to distance travel. So EMF will be induced only when there is a change of magnetic flux. Okay, when this loop will come out this magnetic field, when this loop will come out of this magnetic field, then EMF will induce. Okay, so EMF is inducing, and for how much time EMF will induce? Till the loop is completely outside the magnetic field, and from completely inside the magnetic field to completely outside the magnetic field, the distance covered, minimum distance covered will be B. So T is equal to distance traveled upon velocity, which is equal to B upon V. So for how much time EMF will induce? So T equal to 0.02 upon 0.01 equal to 2 seconds. Okay, hence the induced EMF is 2.4 into 10 to the minus 4 volt, for which lasts for 2 seconds. Okay, now case B, motion normal to the shorter side. So this is the diagrammatic representation. Now this direction of velocity is normal to the shorter side, that is width. So figure showing direction of motion of loop, EMF developed is given by epsilon equal to B. Now we have to take the length, value of length which is perpendicular to velocity. Now this B side is perpendicular to velocity, so B L V. So L here is B, small b. Okay, so B small b V. NCERT equation 6.5. Okay, so this is expression for motional EMF, and length is taken such that length will be perpendicular to velocity. In case B, velocity is perpendicular to this B, so B will be taken. So after substituting all the values, epsilon equal to 0.3 into 0.02 into 0.01. So epsilon will be equal to 0.6 into 10 to the minus 4 volt. So this amount of EMF will be induced in this case. And for how much time? We are going to calculate it. Now, to completely come out of this magnetic field region, the loop have to cover minimum of L distance, okay, along this velocity, L distance. So time taken to travel along length, T is equal to distance traveled upon velocity, which is equal to L upon V. So T is equal to 0.08 upon 0.01, which is equal to 8 seconds. So EMF, induced EMF is 0.6 into 10 to the power minus 4 volt, which lasts for 8 seconds in this B case. So next question, a 1 meter long metallic rod is rotated with an angular frequency of 400 radian per second. This question is similar to the example, one example which we have done in the theory section also. Okay. So 400 radian per second about an axis normal to rod passing through its one end. We have done also, we have discussed one example also about spokes of the wheel. Okay, this is similar to that. So one end of the rod is in contact with the circular metallic ring. A constant and uniform magnetic field of 0.5 Tesla parallel to the axis. Axis is normal to the metallic ring, or we can say normal to the loop. And magnetic field is parallel to the axis, means magnetic field is also perpendicular to the loop and metallic ring. So calculate the EMF developed between the center and the ring. That means across both ends of the rod. One end of the rod is at the center of the ring, one end is at the circumference of ring. Okay, so I will give you some time to think about it. So let's see the solution. Length of the rod is given, which is equal to the radius of ring. Okay, because one end is at the center, one end is at the circumference. So length of the rod is equal to radius of the ring, which is equal to 1 meter. Angular frequency omega is 400 radian per second. Magnetic field B is equal to 0.5 Tesla. So direction of uniform magnetic field parallel to the direction of magnetic field is parallel to axis of rotation. The rotation axis is normal to the rod also. EMF needs to be calculated between center and the ring. So this is the diagrammatic representation. This diagram is from example also. Okay, so we have discussed this example also. So this problem is similar to that. So there is a rod, it is rotating. This is a metallic ring. Okay, one end of the rod is at center of the ring and one end is at the circumference. Okay, so figure representing metallic rod placed between center and circumference of the ring. When a rod rotates in the magnetic field, free electrons in the rod experience Lorentz force. Okay, so at any instant, linear velocity will be tangent to the point. So tangent to Q point. So align your fingers in the direction of velocity. So it is moving anti-clockwise. So direction of velocity will be in this direction. Okay. So align your fingers in the direction of velocity and curl them towards magnetic field, which is perpendicular to the plane and inwards. Okay. So thumb will give the direction of the force. So thumb is towards O, center. But here free charges are electrons. This is metallic rod. So minus Q will be there. So direction of force will be reversed for electrons. It will be towards Q. Okay, so hence electron move towards the outer end of the rod, means towards Q. Separation of charges generates an EMF across the ends of the rod. So separation of charges is there, EMF is induced. Now we will do derivation again. Okay, so let's suppose there is a small element on this rod, dr, at a distance r from the center, small r, at a distance small r from the center O. Okay, so magnitude of the induced EMF DE across a small length dr of the rod is DE is equal to, according to motional EMF, it will be BVL. So L here is small element length is dr. So small EMF induced is DE equal to BV equal to, what is V in the terms of omega? V equal to omega R. So put this in the equation. So B omega R dr. Okay, this is a small EMF induced. Now we will find the total EMF across the rod from center R equal to 0 to R equal to L across the whole length. So epsilon is equal to integration d epsilon equal to, what is d epsilon? Small EMF induced will be equal to B omega R dr from integrating from 0 to whole length L, which is equal to B is constant, angular velocity omega is constant. It will come out. So in the integration it is R dr. So integration of R dr is R square upon 2. So epsilon is equal to B omega R square upon 2, limits from 0 to L. After putting limit, it will result into 1 by 2 B omega L square. Okay, now we'll put the values and find the EMF induced in the metallic rod. So after substituting all the values, epsilon is equal to 1 by 2 into 0.5 into 400 into 1. So epsilon is equal to 100 volt. Hence EMF developed between the center and the ring will be equal to, so L square, L is 1, 1 square 1. Okay. So that's why half into 0.5 into 400 into 1. So epsilon is equal to 100 volts. So EMF developed between the center and the ring is 100 watt. Now, this question, a horizontal straight wire 10 meter long extended from east to west. So this horizontal straight wire is extended from east to west and it is falling at the speed of 5 meter per second. So length is along east to west. Speed is along downward direction. So velocity, or we can say speed, is perpendicular to the length. Okay. At right angles to the horizontal component. Now it is falling at the right angles to the horizontal component of Earth's magnetic field. Now Earth's magnetic field is from south to north. Okay. So magnetic field is south to north. Rod is extended in the east to west direction and speed is in the downward direction. Okay, all the three things, magnetic field, length and velocity, are mutually perpendicular to each other. So magnitude of magnetic field is also given 0.3 into 10 to the minus 4 Weber per meter square. So A part, what is the instantaneous value of EMF induced in the wire? B part, what is the direction of the EMF? C part, which end of the wire is at higher electric potential? So I will give you some time to think about it. So let's see the solution. Length of the wire is given L equal to 10 meter. Falling speed V is given 5 meter per second. Magnetic field strength is given B equal to 0.3 into 10 to the minus 4 Weber per meter square. Wire orientation is east to west, horizontal. And direction of fall is vertical at right angles to the horizontal component of Earth's magnetic field. And Earth's magnetic field is from south to north. Now, magnitude of EMF induced in the wire is E equal to BLV. Now, this BLV is applicable when all the three B, L and V are mutually perpendicular to each other. And in this question, they are mutually perpendicular to each other. So, epsilon equal to BLV, NCERT equation 6.5. So, after substituting all the values, epsilon is equal to 0.3 into 10 to the power minus 4, that is B, into L is 5 meter, uh, that is velocity 5 meter per second, and into 10, that is length 10 meter. So epsilon is equal to 1.5 into 10 to the power minus 3 volt. Okay. Now, how can we find the direction? Direction of EMF can be found using Fleming's right hand rule. Okay. So what is Fleming right hand rule? If you hold your right hand with your thumb, index finger and middle finger mutually perpendicular to each other. Okay. With your thumb representing the direction of the motion of the conductor, which is in the downward direction. Motion of the conductor is in the downward direction in this case. So your thumb is representing the direction of motion. Your index finger representing the direction of magnetic field, which is from south to north. You have to make the graph. You have to make the directions north, south, west, east. Okay. So motion of the conductor is in downward direction. Index finger is representing direction of magnetic field, which is from south to north. Then your middle finger will point in the direction of induced current. So middle finger is pointing in the direction from west to east. If I hold my right hand in such a way that thumb points in the downward direction, index finger from south to north, then this index finger will represent the west to east direction. So this will represent the direction of induced current, like this. It is shown in the diagram also. So thumb will represent the direction of thrust or motion. Magnetic field will be represented by index finger, and middle finger will represent current direction or EMF. Okay, using Fleming right hand rule, it can be inferred that direction of induced EMF is from west to east. So now, what is the direction of induced current can be found from west to north? What is the polarity of EMF? So in the direction of induced current, positive terminal will be formed, because current seems to be generated from the positive terminal. Okay, so current is from west to north. So in west to east. So in the side of east, positive terminal will be there. In the side of west, negative terminal will be there. Okay, at west, there will be negative terminal. At east, there will be positive terminal. Okay. So current means a battery will be, means a hypothetical battery will be there. Okay. So if current is flowing from, let's suppose current is flowing from left to right on the screen, from left to right. So I will make a hypothetical battery. So positive will be on the side of right and negative will be on the side of left. That means current is flowing from positive terminal, that is from left to right. Okay. Similarly, from west to east. So on the east side, there will be positive terminal. So eastern end of the wire will be at higher potential. Okay, next question. Current in the circuit falls from 5 ampere to 0.0 ampere in 0.1 second. If an average EMF of 200 volt is induced, give an estimate of the self-inductance of the coil. So you know the relation between induced EMF and self-induction. So I will give you some time to think about it. Initial current I1 given 5 ampere. Final current 0 ampere. So change in current I1 minus I2. We are going to use the induced EMF or all the expression in the magnitude only. Okay, we are not taking negative sign. That's why we have taken the change in current also positive. Okay, so di is I1 minus I2, which is 5 ampere. Change in the time taken for the change, dt is equal to 0.1 second. So average EMF epsilon is equal to 200 volt. So for self-inductance L of the coil, we have the relation for average EMF as epsilon equal to L di by dt. So this is the relation between EMF and self-inductance. That is NCERT equation 6.14. So L will be from this equation, L after rearranging this equation, L will be equal to epsilon upon di by dt. So L will be equal to 200 upon what is di, what is the change in the current, 5. What is dt, change in time, upon 0.1 second. So 0.1 will go in numerator. So 200 into 0.1 upon 5. So L will be equal to 4 Henry. That is, hence the self-inductance of the coil is 4 Henry. Okay, next question, next exercise. A pair of adjacent coils has a mutual inductance of 1.5 Henry. If the current in the one coil changes from 0 to 20, it is similar to previous question. Okay, but here in the place of self-inductance, there is mutual inductance. If the current in one coil changes from 0 to 20 ampere in 0.5 second, what is the change of flux linked with the another coil? Okay, we have to find the change of flux linkage. So I will give you some time to think about it. So mutual inductance of pair of coils is given M equal to 1.5 Henry. Initial current I1 is 0 ampere. Final current I2 is equal to 20 ampere. So change in current will be di equal to I2 minus I1 equal to 20 minus 0 equal to 20 ampere. So time taken for the change dt equal to 0.5 seconds. Induced EMF in the other coil. So we know that induced EMF due to the change in flux to it is given by epsilon equal to d phi b upon dt. So rate of change of magnetic flux, that is NCERT equation 6.3. And what is the relation of mutual inductance and epsilon? We will also see it, where d phi b is the change in the flux linkage with the coil. EMF is related with mutual inductance as epsilon equal to m di by dt. This is similar expression to the self-inductance expression. Only in place of L, self-inductance, there will be mutual inductance, M. Okay, so epsilon is also represented by rate of change of magnetic flux. So d phi b upon dt equal to m di by dt. So after substituting and simplifying, dt and dt will remove from both sides. So d phi b will be equal to m di. So m is 1.5, di is 20. So d phi b will be, that is, change of flux linkage with the another coil will be equal to 30 Weber. So hence change in the flux linkage is 30 Weber. Got it? Similar question to previous one. So this is all about today's lecture. I hope you enjoyed the session. Thank you.